This problem deals with a porous wall tubular reactor, and we might look at this as a simple version of a membrane reactor. So we have a liquid phase reaction and essentially a plug flow reactor, A goes to B type reaction, isothermal, and then through the wall we have an inert C that's diffusing at a rate of 1.5 cubic centimeters per second for every centimeter of length of the reactor. We feed in pure A to the reactor, we're given the concentration, the volumetric flow rate, given the rate constant, first order reaction, we're going to assume it's plug flow, given a diameter reactor. The question is, what length of reactor do we need for 60% conversion? And in the model, of course, we have to take into account that we have this inert flowing through the reactor, diluting our reactant, and also speeding up the flow through the reactor. So the first thing we do for any problem is draw a diagram to represent the process. So we have a plug flow reactor, certainly not to scale. The outlet conversion, 60%. Here's the rate expression. We have this flow of inert through the walls. It's 1.5 cubic centimeters per second for every centimeter of length. We have the inlet condition, and we're treating this as a plug flow velocity profile going through the reactor. And so essentially now what we don't know is L. So this is our unknown. It's isothermal, and so all we have to deal with is a mass balance. And what we're going to do is a mass balance on our reactant. We'll write this in terms of flow rate of A. So one way to write is for the volume, the cumulative volume of the reactor, which is this cross section of the reactor times the distance down the reactor. And the right side then is a rate constant times the concentration. So this is the rate per volume. And to put things in the same units, we'll write the concentration as the molar flow rate over the volumetric flow rate. So the important thing here that we have to keep in mind is the volumetric flow rate is changing. So the volumetric flow rate is the inlet volumetric flow rate plus the 1.5 times Z volumetric flow rate per second per centimeter. So the units are consistent here. And now we're going to substitute the volume in here. And so with this equation, just rearranging, substitute the volume, you can now separate variables and have the molar flow rate on the left and K times the area dz over the volumetric flow rate. And then we're going to integrate this from an inlet concentration until 60% conversion, which means 40% not converted. And this is from Z equals 0 to the length L. And L, of course, is what we're solving for. So we can integrate the left side is just a log of the flow rate between these two limits. The right side, K, and the cross-sectional area are constant. It's the log of this term in denominator divided by 1.5 here. And again, the limits. So we make the substitution. We have the limit substitute this FA0 cancels the first order reaction, so that's going to cancel. We need the area, the cross-sectional area is pi times the radius squared, which is pi times 1 centimeter, so pi is in centimeters squared. We can then substitute in the numerical values. This left side is the natural log of 0.4, right side the rate constant 0.30, the area is pi 0.5, and the log of 20 plus 1.5 L over 20. Easiest way we want to check to make sure units are consistent, we can look here and see that we have molar flow rate divided by molar flow rate, so the left side is dimensionless. The right side we have an area times Z, so that's a volume, and then the rate constant is inverse time, so this is volume per time, cubic centimeters per second, and of course V0 is cubic centimeters per second, so the right side is also dimensionless. As long as we keep the same units as in our problem statement, the units in the problem are consistent. So we can substitute in the values here due to calculations. So this shows the rearrangement of the equation, and this left side is 1.45, so we're going to take the exponent both sides. Well, it's actually minus 1.45. The log of 0.4 is negative. And so the minus signs are going to cancel. And then we're going to take the exponent of both sides, and this is 4.30, so 3.30 is 0.075 times the length, and we end up with a length of 44 centimeters for this porous wall plug flow reactor. If we had not taken into account the flow rate through the walls, then this length would have been significantly shorter, because we can look at it two ways. The inert is diluting our reactant and therefore decreasing the rate of reaction, or you can look at it, we're decreasing the residence time in the reactor because the volumetric flow rate is increasing as we move through the reactor.